Hi, today we're going to learn about stoichiometry, which is just really the math of chemistry. So, before we start talking about that though, I want to take just a second and review a couple of things we learned about previously. The first thing that's important is we remember how to write the chemical formulas for some different compounds. Okay? If you remember covalents were the ones where we used the prefixes. So here I have dinitrogen trioxide. That just tells me that there's 2 nitrogens and 3 oxygens. So that would be written as N2O3. The next one we had was organics. Pent tells me that there's 5 carbons. Okay, so carbon, 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 carbon. And the ane tells me that all those carbons are single bonded. So they all have a single bond in them. Now, after that, we fill everything else in with hydrogens. Okay, there they are. So if I take a second to count these, I see that it's C5, and then I count around there and I have 12 hydrogens. So the formula for that one is going to be C5H12. The next one I have is ionic. Those are some of my favorite. They're going to be a cation with an anion. The cation in this case is aluminum. Aluminum is 3+. The oxide, oxygen, is 2-. Well, I have to balance ionic, so I balance them by doing my little crisscross method. And so in this case, I end up with Al2O3, and that'll look like this. We have a few more that we did, and I want to go over those as well. We have polyatomic ionic. Polyatomic ionic's really just like ionic, except I have a group that's covalently bonded, but it acts like an ion, okay, and that's nitrate in this case. So let's look at what it will look like. First, I've got Pb, which is lead, and it's 2+. And then I've got NO3, which is negative. Well, I have to do my crisscrossing, and it turns out I've got 1 lead, but I've got 2 of these nitrate groups. And since I have 2 of these groups, I'm going to have to use parentheses around it so that I see it's 2 of all of it. And that will look like this when I write it. Perfect. Okay, next thing I have is a binary acid. The hydro in front of here and the ic acid tells me that. All I'm left with is the chlor, which is short for chlorine. And since it's -1, it's going to attract 1 hydrogen, and I popped it up a second ago. It's going to look like this. The last one is going to be my sulfuric acid. Remember, these acids, my oxyacids, are the ones where I ate so much that I got sick, and the dog bite us. Alright, so with that, I see the ic acid. And since it's ic acid, it must have started as an 8. Okay, so I'm looking for sulfate. Sulfate is SO4, and it's 2-. So it's going to attract 2 hydrogens, and it will look like this, H2SO4. Now, if this was sulfurous acid, the dog bite us, I would look for sulfite, okay, and it would look slightly different. Now, once we got through writing all those different formulas for the different compounds, we had to go through and we had to write an equation. So we started with something like this, and we just did pentane. Oxygen's kind of a hard one, because if you guys remember, we have those diatomic elements, okay? Remember, our saying is, I brought clay for our new home. There's the 7 diatomics, and anytime we see these elements written by themselves, there's going to be 2 of them. So oxygen we're going to have to show as O2. Carbon dioxide is a covalent, so there's 1 carbon, 2 oxygens, so CO2, and water we all know. So I'm going to write that equation, and it'll look something like this. Once I've written that equation, I'm not quite done. We need one more step to the equation. And what that is we have to make sure we follow the law of conservation of mass. The law of conservation of mass states that the mass of my reactants has to equal the mass of my products. More specifically than that, I'm going to say every atom of every element on this side, I have to have the same number of atoms for that element on this side of the equation. Okay, that's the way it's truly balanced. So Here's an example. Carbon, I have 5 of them on this side, but I only have 1 on this side. Now I can't go changing the compound's formula, right? Because I can't change the compound itself. I can use coefficients to balance it. So since I have 5 carbons on this side and only 1 on this side, I'm going to put the coefficient 5 here. Now I've got 5 carbons, 5 carbons. That's happy. I've got 12 hydrogens on this side and only 2 on this side. So I'm going to put a 6 here, and now I have 12 hydrogens and 12 hydrogens. The last thing I need to balance is my oxygens, but I got 2 groups that have oxygen on this side of the arrow and only 1 group on this side. So I'm going to start over here. 5 times 2, I have 10 oxygens right here. 6 times 1, I have 6 oxygens right there. So on this side of the equation, in the product side, I have 16 oxygens. Well, I only have 2 on the reactant side, so I have to put this here, and now I've got 16. So now this equation is balanced, and everybody's pretty happy. Good. Now that we have balanced equations, we can start talking about stoichiometry. The first thing we need to do stoichiometry is we need a balanced equation. Well, here's our balanced equation, the one we just balanced, and we're going to use this for all the lessons that we learn in stoichiometry. Now, what I want you to do is I want you to remember that all these coefficients only represent relative numbers of moles of reactants and products, right? They don't mean that there's 8 molecules of oxygen makes 5 molecules of carbon dioxide. No. What it means is this is a ratio. So for every 8 moles of this, there is going to be 5 moles of CO2. And we need to understand mole ratios. Man, we've been talking a lot about moles, and I remember talking about it early in the year. What on earth is moles? Let's see, it seems like moles were the amount of a substance that it takes to have 6.022 times 10 to the 23rd atoms. Holy cow, that's a big number. How could that help us? Well, here's the problem. If I just grabbed 8 grams of oxygen and 5 grams of CO2, well, CO2 is pretty heavy compared to oxygen. So I wouldn't have a lot of carbon dioxide, but I'd have a lot of oxygen, and they wouldn't mix evenly, and I'd have a lot of oxygen left over. So instead I have to convert everything to moles so that I have the same number of particles. That way I don't have any left over on either side. Before I can change one substance to another using a mole ratio, I have to have it in moles. So let's look another step further. We're actually going to figure out what some of these mole ratios are, okay? And then we'll put them to a little bit of use. So if I wanted to convert a substance from oxygen to carbon dioxide, I would need the mole ratio for that. Now the mole ratios are really just the coefficients, okay? They're not real hard. So here we go. 8 moles of O2 will equal out to 5 moles of CO2. Well, that's pretty good, but since these two are equal, I could actually flip them the other way if I wanted to as well. 5 moles of CO2 are equal to 8 moles of O2 in this equation. Perfect. Now, why can I flip them either way? It may help us later on as we cancel out. Okay, but that's the mole ratios for oxygen to carbon dioxide in this combustion reaction. Let's look at one more mole ratio. Let's look at pentane to water. Okay, well, if there is no coefficient there, we have to assume that the coefficient is 1. Okay, I've got 1 mole of pentane. Okay, and then I've also got 6 moles of water. So let's go ahead and write a couple of them. 1 mole of pentane is going to be equal to 6 moles of water. Perfect. Or I could reverse it. 6 moles of H2O is equal to 1 mole of pentane. Oops. Let's make that a 5. There we go. Okay, so that's my 2 mole ratios for that. Good. So we know how to do mole ratios. The next thing we want to do is see how we would apply this to convert something. So here's an actual equation like you would see. Okay, how many moles of oxygen would I need to produce 15 moles of CO2? Well, let's always start by writing down what we're given. And in this case, we're given 15 moles of CO2. So I'm going to write that right here. 15 moles of CO2. Perfect. Now, I need to convert CO2 to moles of O2. Well, mole ratios help us change from one substance to another. And since I'm going from CO2 to O2, I'm going to use these two as a mole ratio. Now, if you remember from before, I could put this either way. I could put 8 moles of oxygen on top of 5 moles of carbon dioxide, or I could put 5 moles of carbon dioxide over 8 moles of oxygen. But I want carbon dioxide to cancel out. So since carbon dioxide's on top here, if I want it to cancel out, I have to put carbon dioxide on the bottom here. So I'm going to write 5 moles of CO2 is equal to 8 moles of O2. Perfect. Moles of CO2 cancels with moles of CO2. I'm left with moles of O2. And since that's what I wanted to come up with, my work is done. The last step is going to be to get out my calculator, and remember, I multiply everything on the top together and I divide by everything on the bottom. So 15 times 8 equals, divided by 5 equals, and if I hit it all in correctly, I'm going to end up with 24 moles of oxygen. Good. Let's do another one real quick. All right, this one asks me how many moles of water would I produce if I started with 1.5 moles of oxygen. Again, I'm going to start with what I'm given. And I'm given 1.5 moles of O2. Good stuff. Let's see if I can make my lines a little straighter here. So I'm going to do a mole ratio. Since I'm in moles and I'm getting to moles, the mole ratio will work perfect. Now, I want to get from oxygen to water. Since oxygen's on top, I want to put my mole ratio for oxygen on the bottom here, so it'll cancel out. So 8 moles of O2 is equal to 6 moles of water. Perfect. Moles of O2 is gone. Moles of O2 is gone. I'm left with moles of water, which is what I want to be left with. So it seems like I did my equation correctly. The last step is to get out my calculator and multiply 1.5 times 6. Once I do that, I'm going to divide it by 8. And if I do it correctly, I'm going to come up with 1.1 moles of water. Great. Now, most of you guys are saying, that's easy, Mr. Miller. I can do that like nothing. That's not even work. Well, the problem is when I go to actually do that and I go to weigh out 8 moles of carbon, well, it turns out my scale doesn't weigh in moles. That's not too good. And remember, I can only use my mole ratio when the compound is in mole units. And on the other hand, the new substance is going to come out in mole units. So to make this mole ratio applicable, to make it so I can use it in the lab, I have to have a way of getting from grams to moles and moles to grams. And if you guys remember, we did that, okay? And the way we did that, and that was a long time ago, is we calculated molar masses. Remember that 1 mole of a substance, right? 1 mole of a substance is equal to whatever its atomic mass is in grams. In other words, if I had 40.078 grams of calcium, I would have 1 mole of calcium. And therefore, I would have 6.022 times 10 to the 23rd atoms of it. Okay? It gets a little more complicated when we talk about compounds. Right? But let's talk about a couple of those. So, if I need to calculate the molar mass of pentane, I've got 5 atoms of carbon in there and 12 atoms of hydrogen. So here we go. Carbon, each single atom of it weighs 12.01 times 5, because I have 5 of them, and that gives me 60.05. Every single atom of hydrogen weighs 1.01, and I've got 12 of those, so that equals 12.12. Now all I have to do is add those together, and it turns out that the molar mass of pentane is 72.17 grams per mole. In other words, every single mole of pentane weighs 72.17 grams. Good. There's my molar mass of pentane. Oxygen is a little bit easier. Oxygen is O2. Well, every atom of oxygen weighs 16. I multiply that by 2 because it's O2. And that gives me 32 grams per mole of oxygen. So every mole of oxygen is going to weigh 32 grams. Great. To speed things up, I went ahead and gave you the molar mass of each of these compounds in our equation. Now let's see if we can do some little higher level stoichiometry. This time, I'm going to start out with 100 grams of oxygen. And I want to get that to moles of CO2. Well, that's perfect. Always start by writing down what you're given. And I'm given 100 grams of oxygen. Good. Well, that's great, except I can't put grams into my mole ratio to change it to CO2. Instead, I'm going to have to use molar mass. Molar mass doesn't change substances. All it does is change a substance from grams to moles or moles to grams. But it doesn't change substances. Mole ratio has to go in as moles and it's going to come out as moles, but it changes from one substance to another. So the first thing we'll have to do is molar mass. The molar mass of oxygen is up here somewhere. There it is. It's 32 grams for every 1 mole. Well, I could put 1 mole on the top and 32 grams on the bottom, or I could put 32 grams on the top, 1 mole on the bottom. Since grams is up here, I want it to cancel out with grams, so I'm going to have to put the grams down here. So it turns out that 32 grams of oxygen is equal to 1 mole of oxygen. Perfect. Grams will cancel, and now I'm in moles of O2. Well, I don't want moles of O2, I want moles of carbon dioxide. So, once I'm in moles, I can put it into a mole ratio to change substances, which is fantastic. So here I go, I'm going to change substances by using a mole ratio. So, moles of O2 compared to moles of CO2. Since oxygen's on the top, I want oxygen on the bottom. So 8 moles of O2 is going to be equal to 5 moles of CO2. So now my moles of O2 cancels, my moles of O2 cancels. Perfect. I'm left with moles of CO2, and I want to be left with moles of CO2. So it seems like my work's done. All I got to do now is get out my calculator and multiply 100 times 5 equals, and I divide by everything on the bottom. So divided by 8 equals, divided by 32 equals. And when I'm done with that, hopefully, I come up with 1.95 moles of carbon dioxide. Good. Let's try another one. This time, I'm getting 4 moles of pentane to start with. And I want to get to grams of water. So I write down what I'm given to start, 4.0 moles of C5H12. Good. Since I'm in moles, I can put it right into the mole ratio and change it to the other substance. So I'm trying to get from pentane, which remember is a 1, to water, which is a 6. I want pentane on the bottom, so 1 mole of C5H12 is equal to 6 moles of water. Perfect. Moles of pentane goes away, moles of pentane goes away, and now I'm in moles of water. But I look, it doesn't want grams of water. Well, if you guys remember, molar mass doesn't change substance, but it changes it from moles to grams or grams to moles, which is what I need to do. So what is the molar mass of water? Well, the molar mass of water is 18.02 grams per mole. So here we go. Since moles are up here, I want moles on the bottom, and 1 mole of water is equal to 18.02 grams of water. So my moles of water cancels, my moles of water cancels. I'm left with grams of water, and that's exactly what I wanted to be left with. So I'm done. Get out the calculator. 4 times 6 is 24. 24 times 18.02 is something I can't possibly do in my head. Equals, divided by, and all I got down there is ones, so I'm done. And if I hit that in the calculator correctly, hopefully I come up with 430 grams of water. Now I saved the best for last. Okay. The hardest one you guys can come up with in this is to go from grams to grams, because you're going to have to use two different molar masses and 1 mole ratio in between. Okay, so let's look at this equation. I always start with what I'm given. So I'm going to write that down first. I'm given 250 grams of CO2. I'm going to try to write small in this too. Okay. Now, since it's in grams, I can't put it right into a mole ratio. Instead, I have to convert it to moles. So I need my molar mass of CO2. My molar mass of CO2 is 44.01 grams for every 1 mole. Since grams is up here, I want grams down here. And I'm going to go 44.01 grams is every 1 mole of CO2. Good. Grams of CO2 cancels, grams of CO2 cancels. I'm left with moles of CO2. Now that I'm in moles, I can change it to a different substance. So I want to go from CO2 to C5H12. There's CO2, there's C5H12 or pentane, and it's a 1. So since CO2 is up here, I'm going to put CO2 down here. So 5 moles of CO2 is equal to 1 mole of C5H12. Perfect. Moles of CO2 cancels, moles of CO2 cancels. Now I have moles of pentane. But I want grams of pentane. So I got one more step to do. I've got to use my molar mass of pentane to convert it from moles to grams. Well, this time I got moles up top. So I want to make sure my mole's on the bottom. So 1 mole of pentane, C5H12, equals 72.17 grams of pentane. Good. Moles of pentane cancels, moles of pentane cancel. I'm left with grams of pentane, and that's what I want to be left with. So I've written my equation correctly. The last step I have to do is I have to multiply. So 250 times 72.17 equals, I divide that by 5 equals, I divide that by 44.01 equals, and if I do it correctly, I'm going to come up with 82.0 grams of pentane. Well, there you have stoichiometry. It seems hard at first, but we'll do a lot of practice. The more you practice, the easier it'll get. Good luck with your study, guys, and thank you for watching this presentation.